Hello and welcome to the 38th lecture. So today we're going to be talking about volumes by cylindrical shells. And the best way to motivate this is to do the following example, or any one of the following type examples that demonstrates the limits of the methods that we've been using so far. So let us take the following question. Suppose we have this function. Okay. And we want to find the volume obtained by rotating the region between y and the x-axis around the y-axis. Okay, so as always, we start by drawing a picture. So for very small x to the 3 is a lot smaller than x squared. So this thing is going to start by lifting off, but as x increases, this thing will dominate. It's going to cross through 0, and it's going to go negative, right? So it's going to go up and down, right? So something like this. Yeah, and when is it going to cross? It's going to cross when 2x to the 3 equals, 2x squared equals x to the 3, which is going to happen either when x equals 0 or when x equals 2. So here we are crossing at 2. And we put an arrow to indicate how we are rotating things. Yeah? So if we do this, then, as you know by now, the natural thing to do is to slice it like this, with horizontal slices. But if we attempt to do this procedure, then the slices, of course, are all defined by y, right? And if we draw a picture of the slice, what does it look like? We can see it looks like a washer shape. Yeah? With the inner radius being this thing, and the outer radius being this. This we've learned well. Yeah? So if we attempt to do our previous procedure and find these inner and outer radii, then we have a bit of a problem, because how do we do it? Normally we would try and write this graph as a function from the y-axis, which would mean solving things, writing things in terms of y, so trying to solve x in terms of y. But if we try and do this, we just won't succeed. Algebraically, you won't get it anywhere. And you can even see from the picture that there isn't any way to write this graph is a function of the y-axis, because it's not even a graph. Every horizontal line, there are multiple points that cut, there's 2 points that cut through it. So we're never going to be able to write this as the graph of a function of the y-axis. It's just not true. So we can't do this. We can't do this procedure. There are workarounds. We could cut things down the middle, and then one half will be a part of a graph, and the other half will be part of another graph for another function. But it'll get pretty complicated. And it's easy to cook up examples where the workaround you could come up with won't work. So basically, we need another method. In short, we need a better method than slicing, because slicing won't do it for us. Huh? And this is where volume by cylindrical shells come in. This is the second method, and actually, this is the last topic you will need before the exam. So this is how we're going to motivate this. This is how we're going to do this. So the original slicing method I motivated by talking about buying a gourmet sausage which is sold by volume, and wanting to check that you actually have the volume you bought by cutting it up into slices and working out the volume of each slice. Yeah? We can't do that. We're going to have to come up with a different system, but then we're going to have a kind of analogous metaphor, somewhat analogous metaphor. So imagine this thing out here on the table. So it's a rotationally invariant three-dimensional solid shape. Rotationally invariant means that if you rotate it around, it's not going to look any different. Yeah. So let's think of this as a cake, as a gourmet cake, which again is of incredible value, and it's sold by volume. Yeah. And we want to know the actual volume of the cake. Yeah. And its profile is given by some sort of nice function like this, and we want to know its volume. So what can we do? Well, we can get these kind of cylindrical kind of cookie cutters that look like this, right? Which have different radii. Yeah? And we could get a whole set of them which have every radius from 1 millimeter to, say, 10 millimeters. Or 100 millimeters, that'll be better, right? 10 centimeters. Yeah? So you can imagine I have this whole stack of like 100 cookie cutters like this. Yeah? And here is my cake over here. And what I'm going to do is I'm going to take two of these cookie cutters, which are in sequence. So one is just 1 millimeter thicker than the other one. Yeah? So I take whatever the 50 millimeter one and then the 51 millimeter one, and I chop out a cylinder from the center of the cake, yeah, and I pull out the cylinder and I put it on the table, yeah, and I can do that with my entire cake. I can keep chopping it up into these cylindrical shell type things and laying them all out on the table, yeah. And what is cool about those things is that they are things that I can work out the volume of, because the base of these things will just be a shape like this. Let's see how visible this is. The base will just be this. I can do it on the board. The base will just look like this. So let's underline all of this stuff. So we're going to cut things with these kind of cookie cutters, and then if we chop out a piece, it's going to kind of look like this. We attempted a 3D picture of it. Yeah. And so the base looks like this. So if we look directly down onto this thing, it looks like this. Yeah? And the height will be some height that we can measure, right? So the thickness here will be 1 millimeter because we have these cookie cutters that are spaced apart by 1 millimeter. Yeah? So we can work out what the area of the base is pretty easily. It's basically the perimeter times 1 millimeter, right? So if I denote this radius by xi, then the area of base will just be 2 pi xi, and then the thickness of this, which my metaphor I said was 1 millimeter, but more generally we'll just let be delta of x. Yeah? And then this height is some height that I can measure. So sticking to the metaphor, I literally have cut up my cake into 100 pieces that look like this, yeah, and I can work out the volume of each one of them because I can just take a tape measure and measure the height, and I know the radius because that's the radius I chose to cut out with the cookie cutters that I chose. So I know the radius, I know the thickness is 1 millimeter, and I therefore know the area of the base, and therefore I know the volume because I just multiply by the height. Yeah? So I can work out with pretty good accuracy the volume of each one of my individual cylindrical shells. Yeah? And then to get the actual estimate of the cake, then I just add them all together. Yeah? Exactly as in the metaphor of the gourmet sausage. And if you think about this, what we're doing in both those cases is we're doing this strategy of breaking down a complicated, difficult problem into simpler problems by simply cutting things up into smaller pieces where we can understand the smaller piece. Yeah? In the previous case, it was a slice, and now it's a cylindrical shell. Because on the smaller piece, we can understand its volume very, very well. The only error is that this thing isn't quite flat at the top, and this isn't quite the area of the base. There is delta x squared term that we're just going to forget about, because it's so much smaller than this. But those errors disappear as we take more and more pieces. Yeah? So we can do this procedure, yeah? And same as before, it has some inaccuracies, but we can make this more and more accurate by taking more and more pieces. Yeah? And the power of calculus is that we have this way to go from this approximate answer with finite many pieces to actually having an exact answer by having infinitely many pieces because of this more general form of addition, this integration, yeah? Which allows us to add over infinitely many quantities. Yeah? So that is exactly what we did before. In fact, all of the calculus formulas, and you'll learn in multivariable calculus, exactly follow this way. This is what I call the Riemann Sum machine. And it's important we get this clear for ourselves because we're going to have to use the formula that comes out from this in various forms. And there isn't a plug and chug kind of way. Even if I wanted to teach this plug and chug, I couldn't do it because there isn't a plug and chug way to teach this topic. You have to adapt the formula. You have to know what it means in order to do these examples we're going to do later. So let's develop the formula with this metaphor. Let's see what comes out from this. Huh? So we do exactly what we did before. We take a function. When I say did before, we did with the gourmet sausage. We take a function f from a to b, and it's positive. It's into the positive numbers, okay? Which we denote by this. Yeah. Let's draw a picture. This is a. This is b. This is what it looks like. Yeah? This is f. And this thing is going to be rotated around the y-axis. Yeah? And we're going to cut up this base a to b into n equal pieces. Yeah? And now we should be used to doing this. So we let delta of x, this is just the Riemann sum stuff. This is why we teach you Riemann sums. Well, this is one of the reasons we teach Riemann sums, and actually it's the main reason we teach Riemann sums. Yeah. We let x0 be a. We let xi plus 1 equal xi plus delta of x for I is equal to 0, 1, n minus 1. Yeah. And then with this stuff, we have an idea how to express each one of these individual shells for, if this was one of the shells, then this would be xi, then this thickness here is delta of x. Yeah? And then what's the height? The height is basically f of xi. Yeah? So, if we add up all of these shells, we're going to have the sum from I equals 1 up to n, and it's going to be the base times the height. The base is 2 pi xi, yeah, times delta of x. So it's the perimeter times the thickness, and then the height is f of xi. And this is the expression for each one of these shells, and there are n of them. Yeah? And then we want to pass to the limit. We want to let n go to infinity. And what you should recognize is that this is a Riemann sum. Yeah, so it's a little kind of recap of Riemann sums over here. So, Riemann sums. What are they? We first learned about them when we find out the area underneath the graph of some function, right? So this is function g, and we have a to b. We cut it up into equal pieces, right? Same stuff as before. You know, we did all this stuff, and then we approximate the area underneath the graph by these rectangles. We get this expression, the sum I equals 1 up to n g of xi delta of x, where delta of x is, again, b minus a over n. Yeah? And so each rectangle has area expressed by this. It's the base times the height. So if this here is xi, then the rectangle is defined like this. So this here would be the height g of xi, and the base here is delta of x. Yeah? And we see that this expression, this sum of all of these areas of rectangles, tends towards the area underneath the graph, right? So this thing tends towards the integral from a to b, g of x dx. So when you see a Riemann sum, what you should identify is that the delta of x is the base of the rectangle, and the other stuff, which is not the delta of x, is the thing which is defining the height of the rectangle. Yeah? So if we look at this guy, let's just swap these two expressions around so it looks more like the other thing. So then this thing is f of xi, delta of x. This part right here is the part that is defining the height of the rectangles. In the more general picture, we don't necessarily have to have a positive function, so it's going to be the signed height, not a negative height. Yeah. So this thing is the part that defines the signed height. Yeah. So what would be best is if you pause this video for a second and then try and come up with the expression that gives the limit of this as n tends to infinity, or it's an integral. Try and figure out what it is. And again, by far the best thing to do is to pause for long enough, spend at least 5 minutes thinking about it, look at this, then look at this, and try and come up with it. And if you persist, you will come up with this. Do not give up on it. If you give up on this, then you're not getting what you need to get out from this. So do this, give it a good shot. And even only after getting absolutely nowhere, when you have no ideas, press play and then see what I'm about to do. Okay. All right. So what you should come up with is that this thing is actually just the integral from a to b, 2 pi f of x, 2 pi x f of x. dx. Yeah. And formally, you can get this from this by just saying, just let g of x be this other stuff here, 2 pi x f of x. And then you can express this as just g of xi. It's exactly like this. It passes to the limit of this function, which is this function, which is this function. But the formal thing is not how I want you to think about it. I want you to think about it as pictures, and that I want you to recognize that an expression like this is the sum of a bunch of signed rectangles. And this is the signed height, and this is the base, and therefore has to be tending to the integral, which is defined by the height part of the rectangle. That's how I want you to think about it. But nevertheless, we have this. This is our answer, and this is the exact answer. This is the precise answer, because any errors we have vanished in the limit. So this is another tool. It's a completely different formula that allows us to figure out the volumes when we rotate things around an axis. And a couple of things to note. So when we rotated things around the y-axis, using the method of slices, we learned that we're always going to do slices like this, and therefore the slices are defined by the y. Here, when we rotate around the y, then we are going to do shells, and the shells are defined by the distance away from the axis. That will be the radius of the shell, and therefore we're integrating with respect to the x. So it's a completely different variable we're integrating over. Cool. And second thing to note is that this thing is a lot like this thing. It is summing with this generalized summation, this integration, infinite collection of shells with zero thickness, right? Where this is the perimeter of the shell and this is the height of the shell. And that's some of the magic of this stuff. It would seem lunacy to add a bunch of things of zero volume together to get something of finite volume, finite non-zero volume. Yeah, it would make no sense. But we are able to do this because of the power of this machinery, because of the power of these conceptual ideas. We can add this infinite collection of shells which have zero thickness, and therefore zero volume, but we can add them meaningfully together with this generalized version of addition, this integration, to get this correct formula for the volume. This is the kind of yin and yang of calculus. It's this generalized form of addition and this idea of looking at things on a very small scale where they're very simple to understand because basically we're using differentiability. So this yin and yang kind of work incredibly beautifully and powerfully together to allow us to do things like this, to express things like this that we couldn't. We would not be able to do this. We would not get an accurate answer without this, and it's very easy to get an accurate answer with it. And it's I've taught this so many times, right? And I know this very, very, very well. But the power and the beauty of it just kind of strike me every time I talk about it. It's a remarkable creation. This discovery, this thing of calculus, and and it's only the beginning of some much bigger machine that I hope you will learn more about. All right, so this is our formula, and now let's go back to our original question. This is our original question. We have a tool now that allows us to do this. So this is our function. Now we're going to cut this up into shells, right? So draw your picture. Draw the shells you see yourself cutting things up into. And then we just use it. So example completed. So this is our guy, so we'll see what radii of shells we need. So we're going to start here with 0 radius shells. We're going to go up to here, and any further shells, there's nothing. So if we take any cookie cutters of radius bigger than 2 and try and chop out this cake, there's nothing, right? So we're just going to do this from 0 to 2. And then what? Then it's going to be the perimeter. So 2 pi times x times the height of the shell, f of x, dx. This thing is easy for us to understand, to remember, to use, because we know where it comes from, because we have these pictures, perimeter times height. And we know what the f is. Let's replace this by the f straight away, save board space. So our f is this guy, or y. It is 2x squared minus x to the 3 dx. So to pull out the 2 pi, we have 0 to 2. Then we have 2x to the 3 minus x to the 4 dx. And this is 2 pi. And then what is this? 0 to 2. 2x to the 4 over 4 minus x to the 5 over 5. Easy integration. So we have 2 pi, and this will just be a half. So this will be 2 to the 3 here. And this will be 2 to the 5 over 5. 2 to the 3 is 8. 2 to the 5 So 2 to the 4 is 16, so 2 to the 5 is 32, so it's 32 over 5. So multiply this top and bottom by 5, it's going to be 40 over 5, so it's going to be like 8 over 5, here it's going to be 16 pi over 5. And that's it, that's the answer. So the actual calculation, as always, is not hard. Huh? Calculation is just integrating a simple polynomial, setting it up correctly, understanding why this is what you want, which you can see from the picture, huh? is the thing you have to learn, is the new thing. Huh? And obviously we're going to create many more examples which are more intricate, which are harder than this, and that's what we're about to do. But we'll always have to go back to this picture of this is going to be integrating these zero thickness shells. We're going to have to think about what is the radius and what is the height of the shell. Yeah? So take that, keep that clear in your mind as we go forward. Okay, let's do the following example. Find the volume obtained by rotating y equals x, or the region trapped between y equals x and y equals x squared around the y-axis. Okay. Solution. Okay, obviously we draw a picture. So y equals x is this, y equals x squared is this. Yeah? And then this is 1, and this is 1 right here. Yeah? And then we draw our shells. And the shells will have their radius defined by x. Right? So we draw the shell. And the shell is a little bit more complicated now because it is not just the shell which is defined from going straight up from the x-axis up to the height of the function. Right? The shell is actually defined by this. So this is x, the shell's height is defined by this line right here. So visualize the shell. The shell is, I'm going to draw these straight lines first of all. Well, the shell looking sideways on looks exactly like this, right? This is the shell. Yeah? Cool. And if you try and do a 3D picture of the shell, it looks like this. Yeah, cool. So that is the shape that we're dealing with. Yeah, those are the infinitesimal thickness or the zero thickness shells we're integrating up. And we have a shell for every x between 0 and 1. Yeah? So what is our formula? We're going to integrate from 0 to 1, the perimeter, 2 pi x, and then the height. And we have to think about what the height is. Well, this here is y equals x, and this is x squared. So this height right here is going to be x minus x squared, right? So this x minus x squared dx, and this gives us a volume. So this is a simple integration. You know? Pull out the 2 pi, 0 to 1, then we're going to have x squared minus x to the 3 dx. This is 2 pi, 0 to 1, x to the 3 over 3 minus x to the 4 over 4. And then what's this? I mean, this stuff is now pretty straightforward, right? It's 1 over 3 minus 1 over 4. So this is 2 pi 4 over 12 minus 3 over 12. So it's like 1 over 12, so it's pi over 6. Again, the actual integration is easy. If we know what we're actually doing, if we have a meaningful idea of what is going on, right? Which hopefully we do, because we know that this is just integrating up these shells, these 0 thickness shells. So we have the perimeter and we have the height, and we can see it. We can see it. Yeah? So from the picture, this is the correct expression that we just calculated. Okay, cool. Let's do another. Example. Find the volume of the solid by rotating about the x-axis the region under y of x is equal to the square root of x from 0 to 1. Okay. Solution. Again, we draw a picture. So let's put it over here. Our function is square root function like this. Okay. From 0 to 1. So here we are at 1. We are at 1 again. And we're rotating around the x-axis this time. So we're rotating it around like this. Yeah. And we could easily find this by slicing. Yeah. But the point is to do this by cylindrical shells. Yeah. So by cylindrical shells, we have to think. We have to think a little bit. So the volume we obtain from the region under this graph is this region like this, and it's rotated around like this. And we're going to cut it with shells, right? So if this was an in-person class, I would ask you all to show me with your hands what shells we'll be cutting it with. And what I would hope you would do is to do something like this. I'm going to cut it with shells like this. Yeah? And if we do so, if you see that, then you're already on a good start, because if we cut it with shells like this, then we have to think about what variable is going to define the radius of the shell. And what you come up with will be the radius we define by the y variable, right? So this is y like this. Again, we're just working from the pictures. So if we cut it like this, then what do we see? We'll see something like this, right? Which will go down like this. So this is the sideways view of the shell. It probably goes down a bit further. Like this, yeah? And if I try and do a 3D picture, it looks like this. Cool. And then with this picture, we can actually do it. We can actually find out this volume, because, again, we know what we're doing. So we have shells from every radius from 0 up to 1. So integrate from 0 up to 1. The perimeter of the shell, it's 2 pi y. See this? Yeah, and the height of the shell is this thing. This is the height of the shell, right? So to find that out, we have to express the graph as a graph from the y-axis, but that's not hard to do because it is just the square root of x. So we know in terms of y that this distance here is y squared, yeah? And therefore this green line here is going to be 1 minus y squared. Yeah? And that is the height of the shell. Cool. With this in mind, we can just be sure about this. We can feel confident that this is the right expression. This is what you have to be good with. You don't want to be just kind of guessing, just putting stuff down with some sort of vague hope that it's correct. If you draw these pictures and you get confident with this, then you will know that this is correct, and then the actual integration is just trivial. So it's the same thing I've been emphasizing all the time. It's why I explain the formula. It's why we need to see what this looks like. Okay, so yeah, yeah, I guess there's not much more to be said except what I've said already dozens of times. Do it this way. Just do it this way. Don't try and extract an algorithm. Don't try and do it any other way than this way. Draw the pictures. Be sure that you're expressing the pictures in the language of math, and then you're on a solid footing. Okay, so and then we're all set. And this is obviously an easy calculation, right? So then it's just pi over 2 pi, and then this will just be a quarter, like 1 over 4, so it's pi over 2, and that's it. Easy, yeah? Okay, let's do another example. Example 4. Find the volume of the solid obtained by rotating the region bounded by y of x is x minus x squared, and y equals 0 around x is equal to 2. Okay. The picture, as always. Yeah, so this is our function. So what does it do? So for small x, this is a lot smaller than this. It starts off going up and then it goes down. And obviously it crosses at 1. Yeah, this is kind of what it looks like. Y equals 0, that's the x-axis, so the region we're talking about is this region. Around x equals 2, so x equals 2 is right here. 2. Okay, so let's do this dotted line to indicate the axis of rotation. So we're rotating it around here. All right, so we're really going to have to think carefully now. because we don't have the y-axis or the x-axis. We have an axis which is set off, you know, some distance away. So again, we're going to draw the shells. We're going to draw the shells. So we're going to take our cookie cutters and chomp it down like this, and we're going to create a shell like this. We'll have this thing will be the height, and looking sideways it will look like this. I'm going to go off the edge here, and the kind of 3D picture is something like this. Yeah, that is our shell. So, what variable is going to define the radius? Well, since the function is given by this thing here, it's going to be easier to stick with this variable x, which means we can't use x to define the radius anymore. We're going to have to adapt. Yeah? But if we do stick with x like this, then the height is easy because we have it. It's just a function. It's given by x minus x squared. But then we have to think, what will the actual radius of the shell be? What will this thing be? But that shouldn't be hard either, because we just look at the picture, and this is 2, right? So this distance is x, so this blue line is just going to be 2 minus x. Yeah? Cool. So, if we do that, then we start to feel confident, because we know we're integrating up all of these zero thickness shells. Each shell is going to be defined by an x for some x between 0 and 1, right? But now we can't just plug into the formula, because the formula was given when we rotated around the y-axis, right? And so the formula again was this. When we rotate around the y-axis, this was our formula. If we did it from a to b, it was 2 pi x f of x. Okay, just, as I said from the beginning, even if I wanted to teach this plug and chunk, I couldn't, because we can't just plug in numbers into a formula, because we have to understand where this is from to adapt it for these needs. So since we are not able to just use x for the radius of the shell, we have to look at the picture to identify the radius of the shell. And the radius of the shell we see is this 2 minus x. So we're going to use the idea, but not the exact formula. And what we'll come up with, or what should seem reasonable to you, and what you should be able to come up with yourselves, is the following. And here's another moment where it's very good for you to pause, try and come up with an expression for the volume of this thing, using the picture, using what we've learned, using the main idea, which is that we are integrating up these zero thickness shells over all the radii for which they actually exist and give us something. Yeah? So it's going to be the perimeter times the height of all of these zero thickness shells. Let's give them pause, give that a go, give it 5 minutes, then watch what I do. Okay, so I see that I get some non-zero shell for every x between 0 and 1. So I'm going to integrate between 0 and 1. Yeah? And then what is the perimeter of the base of the shell? It's going to be 2 pi, but this here is the radius of the perimeter, right? So it's going to be 2 pi times this quantity, 2 minus x. Yeah? And then what's the height of the shell? I see it from the picture here. The height is going to be x minus x squared. Okay, again, if you are sufficiently convinced that this is a language that describes pictures, and you hold fast to the pictures, then you can feel confident that you are doing something correct here. Now this will work out okay. So we just multiply this through, and now it's just a calculation, right? So it's going to be 2x minus 2x squared, applying the 2 through, and then we're going to have minus x squared plus x to the 3 dx. Well, and then we clean this up. So we have 2x, we have minus 3x here. Minus 3x squared, I should say. And then we have x to the 3. Like this. And now it's just an integration, right? An easy one. Okay, so x squared, x to the 3, x to the 4 over 4. Yeah. And I dropped the 2 pi. And then we put the numbers in. So 2 pi. And then this will be 1 minus 1, and then this will just be 1 over 4. So it's just pi over 2, and that's the answer. Okay. So what you have to learn is to draw this picture and then do this correct formulation using the idea rather than the formula. Yeah? So this is the last topic of this course. It is a topic that historically people find difficult, but I claim it's not difficult. It is not difficult. It is just doing what we've been practicing all this time. So please don't be intimidated by this. Certainly expect to be tested on it because it hasn't been tested yet on the midterm 3. And the final exam will weight the later topics more. It'll be cumulative over everything, but we've done a lot of work on volumes, and we haven't tested it much. So I would expect maybe 2 questions on volumes, perhaps a free response, perhaps a multiple choice, and this would be an excellent candidate for a free response. So do not eject this topic. It'll be worth 15 points off the exam. Just practice it. Just practice it. Watch this video more than once if it's not clear. If it's still not clear, then make notes of what you don't understand. So we have no more in-person classes. I will hold an office hour on Monday via WebEx. I'll send out an announcement. Use that. Practice that beforehand, and use that, and then talk with me if you don't feel comfortable with this. Most of all, practice it. Do the practice problems, do the homework for credit, do the odd-ordered exercises, and you will find that you will get this if you draw these pictures and follow this procedure. Okay, so don't give up on this. It's actually a really nice topic, and yeah, and it's one you can all succeed in. So, all right, that's it for today. Have a great day.